This video will assume you know some calculus, but feel free to pause the video to look up any terms you're unfamiliar with. Today on the Y of Math, we're covering why e to the I pi power equals -1, and what it means to raise something to an imaginary or complex power. To do this, we're going to use a Taylor series. Taylor series allows us to approximate the value of a function, knowing its value and the value of its derivatives at one point. Derivatives measure the rate of change of a function at a given point, so integrating the derivatives of the function allows us to convert any differentiable function into a polynomial. We can generate an approximation that works in the immediate vicinity of the known point by integrating only the first few derivatives, but we can get a precise value for the function by integrating all of the infinite derivatives of the function. Since the starting point is arbitrary, there will be an infinite number of equivalent polynomials we can use, but there is generally one that is the simplest because of the values chosen. Such as if we choose x0 equals 0, then the x0 terms drop out, and functions generally have few well-known values. Case in point, f of x equals e to the x. You know that e to the 0 power is 1, and since e to the x is its own derivative, all of its derivatives at 0 are also 1. That gives us a Taylor series of e to the x equals 1 plus x squared over 2 plus x cubed over 6 plus x to the n over n factorial, and so on. Doing this for cosine of x gives us f of 0 equals 1, f prime of 0 equals 0, f double prime of 0 equals -1, f triple prime of 0 equals 0, and the nth derivative is equal to the n minus 4 derivative. So that gives us a Taylor series of f of x equals 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. Now, since every attribute of the function also applies to the infinite degree polynomial, you can look here. For sine of x, sine of 0 equals 0, g prime of 0 equals 1, g double prime equals 0, g triple prime equals -1, and has the same periodicity as the cosine function. That gives us a Taylor series of x minus x cubed over 6 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. We take the derivative of that, we get 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. And that's just cosine of x. All the properties of the original function are preserved. This allows us to extend the definition of functions outside their normal domains, such as to complex numbers. If we plug an imaginary argument into the Taylor series for e to the x, we get e to the I theta power, and we'll see why I did that in a moment, equals 1 plus I theta squared over 2 plus I theta cubed over 6 plus I theta to the 4th over 4 factorial, and so on. Bring down the exponents. That gives us 1 plus I theta minus theta squared over 2 minus I theta cubed over 6 plus theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial minus theta to the 6th over 6 factorial minus I theta to the 7th over 7 factorial plus theta to the 8th over 8 factorial, which is simply cosine of theta plus I sine of theta, specifying that theta is the angle in radians. Plugging in pi for theta, you get cosine of pi plus I times sine of pi, which is -1, because cosine of pi is -1, sine of pi is 0. Now, what if we want a complex argument? Well, e to the a plus b to the I is simply e to the a times e to the bi. We generally express any complex number, a plus bi, as r e to the I theta. R is equal to square root of a squared plus b squared, and theta is equal to the arctangent of b over a. Now you must remember, if you're using a calculator, to set it in radian mode. If you set it in degree mode, it will not do this correctly. Now, what if we want to use a base other than e? Well, any base a can be rewritten as e to the natural log a power. So a to the I theta power is simply e to the I theta times natural log of a. Thank you. Remember to like, share, and subscribe, and leave any questions in the comments section below. I'll see you next time.